All right, so theorem three kind of leads into the definition, definite integral. So we'll talk about that and move our way down, and that's where we're going. So theorem three says the limit of Riemann sums. So if f is a continuous function on a to b, closed interval, then the Riemann sum for f on a to b approach a real number limit I as n approaches infinity. Now, they said, well, that's a star. So that means the precise meaning of this limit statement is as follows. For each some e greater than zero, there exists some d greater than zero, such that the Riemann sum s of n minus I is less than e whenever the Riemann sum is for f on is a Riemann sum for f on the interval a to b for which delta x is less than d. Now, again, that just means a lot of stuff, but what it really does is it helps us to get this definite integral. So it says, now let f be a continuous function on the closed interval a to b. Now, the limit I of Riemann sums for f on the interval a to b, again closed, guaranteed to exist by this theorem is called the definite integral. And so the definite integral is going to be a little different than what we've been doing before. We've been doing the indefinite integral, and it didn't have any things a or b here. And when we were done, we had a plus c at the end. Well, this time we're going to have a closed thing. We're going to go from a to b. That's because we're going from that interval from a to b, and then f of x dx. And so the integrand is f of x, the lower limit of integration is a, and the upper limit of integration is b. So basically, we're integrating f of x from a to b, and we're going to find the area under that curve doing that. All right. So because area is a positive quantity, the definite integral has the following geometric interpretation. So area from a to b f of x dx is shown as follows. So from a here to b here. Well, notice that a is down here on the negative side, so it's a negative value. B is on the positive side, so it's a positive value. So what happens is we're going to get a negative a plus b. So we're going to get a negative part. We change it to positive, so we know the area between the curve and the x-axis. And this one, we have a positive value between the curve and the x-axis, so we can just say plus b. Okay. So that represents the cumulative sign of the signed areas between the graph of f and the x-axis from a to b. And again, as x equals a to x equals b, where the areas above the x-axis are counted positively and the areas below the x-axis are counted negatively. Okay, so that's why we say, okay, well, we're going to say that's a negative a and that's a positive b. So with that in mind, we can use this figure 9 to help us figure out these areas A, B, and C that they're asking us for. So for A, they want to go from A to 0. Well, A is over here, 0 is here. So we want to find this area here. So we want to find that integral. Well, that says that's 2.3 is the area here. But what is the signed area? Well, the signed area is going to be a negative 2.33, okay? Because there's this area here is given as the positive of it, and we want whatever it is. And since it's below the x-axis, it's a negative. What about B? Okay. Well, B is going to go from 0 to C. So we're going to go from 0 to C. Well, that means we have a positive area here. We have a negative area here. So what we really need to do is we need to take B minus C because here these are all have been converted to positive areas. So B is 10.67 minus 5.63, which is below. And if we calculate that, we get what? 5.04. Okay. And so that's how we're going to calculate that one. What about C from 0 to B? Well, that's just the area of B. So that's just 10.67. And because it's above the x-axis, it's positive, and we only just take that positive area and we're good to go. Okay. All right. That's all I have for this part. Let's come back in a little bit for some more.